Hello and welcome. Today we're going to be discussing Chapter 3, Lesson 1 on exponential functions and their graphs. In Chapter 2, we talked about exponential, polynomial, and rational functions. In Chapter 3, we're talking about exponential and log functions. Now, these are non-algebraic functions, exponential and log functions, and they are referred to as transcendental functions. We're going to start with the parent function, exponential function f of x is equal to a to the x, where a is our base and x is our power. Okay, starting out on page 180, definition of exponential function. We just went over that. We know that a needs to be greater than 0 and not equal to 1. If you think about a being 1 to any power is just 1, and that would give us our constant function. X is any real number. If you look at example 1, it says evaluating exponential functions. Use your calculator to evaluate each function at the indicated value of x. F of x is 2 to the x, 2 to the negative x, 6/10 to the x, and 1 and 0.5 to the 2x. It gives you values to evaluate each of those functions at. I would like you to try exercise 7. I want you to pause the recording and come back to see the results. Please work this problem on your own and then return to the recording. And welcome back. Let's go over those keystrokes. We are looking at the function g of x equaling 5, our base, to the power x, and they want you to evaluate x at negative pi. So one way to think of this is we are replacing every x we see in the function with our value negative pi. This is simply 5 to the negative 3.14. It's an irrational number. We know it's non-repeating, non-terminating. And when we do this, we want to think about this being equivalent to the fraction 1 over 5 to pi, being a very, very small fraction. 1 over 5 to any power greater than 1 is going to become exceedingly small. So that was problem number 7. We're simply substituting values for x, our exponent, and evaluating with the calculator. Please turn with me to the top of page 181. We see example 2. We're going to talk about graphs of exponential functions. It says the graphs of all exponential functions have similar characteristics as shown in examples 2, 3, and 4. We are going to be looking at functions of this form: base a, x, our exponent, and it looks like we are looking at two different bases. It says graph the function f of x is equal to 2 to the x, and f of x, or they said g of x, is equal to 4 to the x. Now, considering the nature of these bases, we can predict that f, the first one, f of x, will grow exponentially, but compared to the second one, will not grow as quickly as the second one, with a larger base, a base being raised to a higher and higher power. So they've shown you these graphs, but what I'd like you to do when you work out these problems is consider tables in order to graph more quickly and understand what's going on. A table of values. So for the first one, we look at critical values. We know that any base to the power of 0 is simply 1. So we're going to substitute that into both of these and then assess further values. Let's look at another domain value, x being 1. 2 to the first power on the first graph, 4 to the first power on the second graph. So that we can see there, just there, that our function 2 is climbing much more rapidly. We can see both functions passing through 0, 1. First graph in purple. And anywhere left of the y-axis, we can see we are going to get increasingly smaller. 1 over 2 to the first. Negative 2 would be 1 over 2 to the second, or 1/4. So as we come from negative infinity, our graph is approaching that x-axis, and as we travel to positive infinity, we can see that our graph, or our range, is approaching positive infinity as well. So at x equals 1, x equals 1, y is 2. If we look at the second graph on top of that first one, we see that they share these similar values, 0, 1. We can see in the case of graph number 2, at 1, our value has increased to 4 already. We have that same behavior on the left-hand side of our graph. We're coming through the same point and then climbing increasingly fast, exponentially, much more quickly than when our base was 2. Let's now take a look at example number 3, the graph of y equals a to the negative x. And if we remember those rules of exponents, we remember and understand that negative exponent indicates that that base is going to become part of the denominator to that positive power. Here's another way to look at it. A negative exponent. We know the rules for same base as a ratio. And I know this. If I take the powers of those same bases, our rule says that we are to subtract. So this one simplified would be 2 minus 3, or a to the negative 1. If we take the ratio and write it out in product form, we can see that we have a times a over a times a times a, and we know that 2 of those are canceling, leaving 1 over a in the denominator. So I hope that helped you understand and remember our negative exponents and what they actually mean. Let's take a look at example 3. It says our bases now are going to be similar to what we had before. We have f of x equaling 2 to the negative x, and we have g of x equaling 4 to the negative x. Well, I'd like you to stop and think, make a prediction. If you're looking at your book, you can see what's going on. But if we go ahead and make tables for both of those, x and y, for our purple graph, x and y table for our red graph, plugging in values for our f of x function, x to the negative, when x is 0, we still understand anything to the 0 power is simply 1. If we put an x to the negative 1, we know that's 1 over 2 to the first power. X is 2. 2 to the negative 2 is 1 over 2 to the second power. What happens when we put in negative values? X to the negative, the opposite of negative 1 is x to the positive 1. And the opposite of negative 2, x to the positive 2, would give us 4. So if we look at a quick sketch of that graph, at negative 1, negative 2, our values, we know that we have a mirror image of the previous example. At negative 1, we're at 2. At negative 2, we're at positive 4. And we can see 0, 1, our y-intercept. And we can see this is a complete and total reflection across the y-axis of our value, or of our function, 2 to the x. 2 to the x, 2 to the negative x. We understand putting a negative value in for x gives us a reflection about the y-axis. So let's take a look at g of x. We know 0 always yields a 1 as a power. X to the negative 1 is 1/4, 1 over 4 to the first. X to the negative 2 is 1 over 4 to the second, 1/16. We can see things getting very tiny, much faster. And let's put some negative values in there. Negative 1, the opposite of negative 1 is 1, 4 to the first, and the opposite of negative 2, 4 squared, 16. So we can see at negative 1, we're up higher and faster on the left as we come in from negative infinity. On the x-axis, at negative 2, we're at 16. So it's much higher slope coming down in. We know we share that point. And we are approaching that x-axis as x becomes infinitely large. Please try right now. Please try numbers 9 and 11 in your problem set. Pause your recording and then come right back and we'll look at the solutions to those. So I've gone ahead and created the tables for problems 9 and 11, and we are comparing 5 to the x and 5 to the negative x. And I plotted these points, understanding x as a positive exponent. For function f of x, we see a huge growth, exponential growth, and we can understand and start to conclude that our negative exponents, we are going to have quick and steady exponential decay. So we can see applications for science and all the biology that we've been doing and loving. And so far, so good. So, Chapter 3, Lesson 1, we have gone all the way through examples 2 and 3. I invite you to, again, review powers of exponents at the bottom of page 181, excuse me. These rules, these power rules, come back to you from a little bit from Algebra 1, but a lot from Algebra 2, so those are noteworthy and should be in your notes for that next test that might be coming up sometime this month. Page 181, Rules of Exponents. Please get those into your notes. And join back here, almost live. We're going to be going over the rest of Chapter 3, starting with example 4, the library of parent function, a to the x, and then we're going to talk about the natural base e. So join us right back here